Hello, I'm Nicholas Newell, an independent researcher in structural bioinformatics. My poster concerns beta turns, which are 4-residue backbone segments in proteins that are the most common type of local protein structure after helices and strands, and play key structural and functional roles. Previous work has developed beta turn classification systems and tools that operate in the Ramachandran space of backbone dihedral angles, which presents challenges for the visualization, comparison, analysis, and design of a wide range of turn conformations and the structures that incorporate them. This work derives a local Euclidean space coordinate system, global alignment, and geometric parameterization for beta turns, and incorporates these features and many others into a suite of complementary web tools for the study of beta turns in their context, available at www.betaturn.com. The first tool, ExploreTurns, is a database selection screen, structure profiler, and graphical browser integrated onto a single web page, which renders a redundancy screen PDB dataset of 102,000 beta turns structurally addressable by a wide range of criteria describing the turns in their local backbone contexts. The tool features a built-in interpreter for a new general nomenclature for short H-bonded loops that classifies all these structures by their component H-bonded turns of lengths 2 to 8 residues, and it supports the analysis and retrieval of these loops, as well as beta hairpins, amino acid sequence motifs, and supersecondary structures. Since beta turns constitute almost 2/3 of protein loops, and ExploreTurns also encompasses the 4-residue backbone neighborhoods of turns, the facility enables the exploration of most loop structure, introducing a turn local coordinate system useful for analysis into the many beta turn contexts. ExploreTurns is applied here to detect multiple new H-bonded loops, including new Shellman loop variants, and a large family of motifs satisfying a new generalized definition of a beta bulge loop. The 6C2 beta bulge loop is displayed here, hosting a triplet sidechain motif. The facility is also applied to map helix cap sequence preference versus cap geometry and investigate the relationship between turn geometry and depth beneath the solvent-accessible surface. ExploreTurns should prove useful in applications such as protein design, in which an enhanced Euclidean space picture of turn and motif structure and the ability to identify and tune structures suited to particular requirements may improve performance. We can demonstrate the tool by selecting sets of motif structures from the motif catalog. We can start with Shellman loops and variants, and start with the classic Shellman loop. Which commonly forms a C-terminal helix cap. We can go on to the wide Shellman loop, which adds a residue inside the Shellman loop's beta turn, forming an alpha turn. And finally, we can look at the short Shellman loop, which subtracts a residue from the Shellman loop's beta turn, forming a gamma turn, and more often is seen forming helix N caps. Next, we can look at several beta bulge loops, starting with the type 1 or 5C1 beta bulge loop, which is the most common. And going on to the 6C2 BBL, which adds a residue inside the 5C1 BBL's bulge. Next, we can look at the 7C3 BBL, which adds another residue inside the bulge. And finally, the 7NC3 BBL, which adds an H bond inside the 7C3's bulge and forms a dual N and C type BBL. MapTurns is a server for motif maps, which are interactive 3D graphical conformational heat maps of the backbone and side chain structure, H-bonding, and context associated with sequence motifs in beta turns. We can demonstrate MapTurns by opening a map from within ExploreTurns. This is a map for the sequence motif that specifies aspartic acid at turn position 1 and arginine at position 3. It's one of the most important salt bridges in beta turns. The first motif map page shows us the backbone and sidechain clusters associated with this motif. We can open the second map page to select the context of the motif in the form of tail clusters formed by clustering the backbones of the turn's adjacent structures. And we can browse the PDB structures in the right-hand viewer. The ProfileTurn tool characterizes the geometry and sequence motif content of a turn uploaded by the user and evaluates the compatibility between the turn's sequence motifs and its backbone conformation based on motif occurrence in the database. We can demonstrate by uploading a turn, which is displayed against the set of backbone metoids for all beta turns and profiled below. We can select a set of structures close in structure to the uploaded turn.